Welcome back to the deep dive. Today we're getting into something really foundational. One of the core blueprints for how computers organize information. We're talking about data structures and, more specifically, abstract data types.
We really are. We're jumping straight into an architectural principle that, it governs how temporary information is stored and managed in pretty much every piece of software you use.
And the specific structure we're zeroing in on today is the stack.
That's right. And our mission, for you listening, is to really understand how one very simple, very strict rule can create such enormous utility in programming.
And that rule, it really is everything. If you take away just one thing from this deep dive, it has to be this: LIFO.
LIFO, last in, first out. That is the core design philosophy. It means the item you put in most recently.
It's the only one you can take out next.
Exactly. Think of it like a tube of Pringles. You can only get the top chip. You can't just grab one from the middle.
And that brings us to this idea of an abstract data type, or ADT. The key word there, I think, is abstract.
It is. Because it's not defined by, the code that builds it. It's defined by its contract, by the operations you can perform on it.
It's the interface.
The interface, exactly. The underlying implementation could be a list. It could be something much more complex. It doesn't matter. What matters are the rules of engagement, and for a stack, those are non-negotiable.
The classic analogy is always that stack of plates in a cafeteria, right?
That's perfect analogy.
The staff puts a clean plate on top, and that is the plate the next person has to take. You can't pull one from the bottom without the whole thing crashing down. That LIFO design is actually the entire point.
It is. And because it's so constrained, the stack ADT really only needs a few core operations. You have your init to start it and len to get the size, but the two that truly define it are push and pop.
Okay, so push is pretty straightforward. You're just adding a new item to the top of the stack.
Correct. But pop is where that LIFO rule really shows its teeth. When you call pop, the system removes and gives you back the last item that was added. No exceptions.
And you can't ask for any other one. If you try, it's not a stack anymore.
You've broken the contract. And of course, this is empty, which just checks if there's anything left. So you have this simple contract. Push on top, pop off the top.
But let's talk for a second about actually implementing this, say, in a language like Python, because how you build it really matters for performance.
Oh, absolutely. This is where understanding the underlying containers is vital. You can use a standard Python list to act like a stack.
Right. You can use .append for your push and .pop to remove.
And that works great because a Python list is really fast at adding or removing things from the end, from the right side. That's what we call an O of 1 operation. Super fast.
But what if your mental model or a specific algorithm needs you to operate on the front of the list?
Then you have a problem, a big one. If you try to constantly insert or remove items at index 0 of a Python list, the performance just tanks.
Because the whole list has to shift over in memory every single time.
Every single time. It becomes an O of n operation, which is incredibly slow if your stack gets big. And that's why our sources really emphasize the better, more specialized tool for this job.
The DIC.
Exactly. The DIC from the collections library. It stands for double-ended queue. And it is specifically designed to have super fast appends and pops from both ends.
So if you're building something for high performance, you skip the list and go straight for the DEC to implement your stack ADT.
That's the pro move. It guarantees your push and pop stay lightning fast no matter how much data you're handling.
Okay, so understanding the LIFO rule reveals the mechanism. But where does this restrictive system, actually give us some incredible leverage?
We see its power immediately when we look at how computers handle something as basic as arithmetic. This is one of the biggest applications for stacks.
This is where it gets really cool, because it shows how we humans made math kind of complicated for computers. We use what's called infix notation.
Right, the way we all learned it in school, 5 plus 2. The operator sits in between the numbers.
Which means we need all these extra rules. Order of operations, parentheses.
Exactly. If you see 5 plus 2, 3, you have to remember that multiplication comes first. To change that, you need parentheses. And computers, well, they hate parentheses and precedence rules. It just slows everything down.
So they prefer a notation where the order is just built in, like postfix notation.
Yes, postfix or reverse Polish notation. The operator comes after the operand, so 5, 2 plus out. And the absolute genius of this is that when you use postfix, you don't need parentheses at all.
Wait, okay, hold on. If there are no parentheses, how does the computer know what to do first in a long expression? It just sounds like chaos.
That's the beautiful part. The stack imposes the order. The LIFO rule itself guarantees the correct order of operations as the expression is read.
This feels like one of those aha moments. Let's walk through an example. What was the one from the notes? It was 512 plus 4 plus pair.
That's a great one. Okay, so remember the algorithm. If it's a number, an operand, you push it. If it's an operator,
You pop two numbers, do the math, and push the result back on.
you've got it. So we read left to right. First up is 5.
Number, push it, stack is 5.
Next is 1.
Number, push it. Stack is now 5, 1.
Next is 2.
Push again. Stack is 5, 1, 2. Okay, and now we hit our first operator, a plus sign.
Right. And that's the trigger. So we pop the last 2 items. That's the 2 and then the 1.
And we do the math. 1 plus 2 is 3.
And we immediately push that result, the 3, back onto the stack. So now our stack looks like 5, 3. See how we just resolved that inner calculation?
Yeah, it collapsed down. Okay, next token is 4.
Number. So we push it. Stack is now 5, 3, 4.
And then we hit the multiplication sign, the curve.
Trigger again. We pop the 4, then we pop the 3.
We calculate 3, 4, which is 12.
Then we put the 12 back on. The stack is simplified again to 5, 12.
And we're at the very end. The final token is another plus sign.
Final operation, pop 12, pop 5. You calculate 5 plus 12, which is 17.
And push the 17 back on. The stack now holds just one number, 17, and we're out of tokens.
And that single remaining item is your answer. The LIFO rule made sure all the nested operations happened in the right order, and the computer never once had to think about parentheses. It's just elegant.
That really is. The strictness of the interface provides this perfect way to control the state of a calculation. It makes total sense why compilers would be built on this.
And that ability to manage temporary states, to enforce this kind of strict ordering, it goes way beyond just math. It's the ultimate undo button.
Okay, let's connect this to some of the real-world programming problems from the source material, because that's where the theory really hits home.
For sure. Take the backspace problem. Imagine you're processing text input. The hashtag character means delete the last character typed.
So if you type ABC stag D, the output should be ABD.
Right. Now, trying to solve that by just manipulating a string is messy. You're constantly moving characters around. But with a stack,
It's perfect, LIFO.
it's perfect. So you see A, you push A. You see B, you push B. Your stack grows to ABC. Then you see the backspace, the hashtag.
And what you need to remove, the last thing you added, the C. So you just pop.
A single pop operation. It's instant. Then you see D, you push it on top, and your final stack is ABD. The state was managed perfectly.
That's a great example. What about something like pairing items?
Another classic. Think of the pairing socks problem, or maybe more relevant for our listeners, checking for balanced parentheses or brackets in code.
Oh, yeah, a huge job for any compiler. Every opening needs a closing.
The stack handles this beautifully. You read the code character by character. Every time you see an opening delimiter, A, you push it onto the stack.
So the stack is kind of holding a promise. Hey, this needs to be closed later.
Exactly. And when you see a closing delimiter, say AA, you look at the top of the stack.
And you check if it's a match. If the top is an opening, you're good.
You're good. They match, so you pop the opener off the stack, you fulfill the promise. But if they don't match, if you see but the top of the stack is, immediately you have a syntax error.
And when you're done, if the stack is empty, everything was balanced perfectly.
Perfect balance. The constraint is what makes it powerful. The fact that the stack can't do anything but interact with the top element is what makes it so fast and reliable for these specific jobs. It's minimalist design for maximum effect.
So to wrap up, we started with this really simple idea of a stack ADT, defined just by push and pop, and this strict LIFO rule.
And what we found is that this very simplicity, this constraint, is actually a source of incredible power in programming. It's the best tool for any problem that involves managing states in sequence, backtracking, or balancing nested items.
It's a great lesson that sometimes adding strict constraints is what leads to the clearest and most efficient code.
Absolutely. And for anyone listening who wants to take this a step further, the real challenge is to try and write a function that converts infix notation, the way we write math to postfix notation.
Oh, that sounds tricky. Taking something like 4-2 plus 3 and turning it into 4-2 plus.
It is a phenomenal puzzle because it forces you to use a stack to hold the operators, not just the numbers. You have to manage precedence rules yourself, deciding when an operator can go to the output and when it has to wait on the stack. It's a brilliant exercise.
That's a great challenge. So try tackling that conversion or look up some of those problems we mentioned, like the backspace problem. Seeing the stack solve these puzzles really solidifies its power.
It does. Understanding these fundamental data structures, It really is the bedrock for writing powerful, efficient solutions that you can use every single day.